In this problem, we have another truss structure that looks kind of like a truncated triangle here. And we're given these lengths, and we're given the these lengths are 2.4 meters. This is 0.46 meters, and this is 2.62 meters. And then we have loads acting on here. On the ends, the loads are 1 kilonewton, and then F2, these are 2 kilonewton. So what we have, we can figure out that the reaction forces here, because of the symmetry in this system, the reaction forces have to be the same, and they have to offset these loads. So that means that they are going to be 4 kilonewtons. So we have these are 4 kilonewtons each on each side here. And then one side is pinned, I guess. This side is pinned, which basically the horizontal reaction is on that side is 0 because there's no applied horizontal loads. And so in the first case, we're asked to find the reactions through CE, DE, and DF, which are these three members here. So then we make a cut right there. And what I've done is, because these things are starting to get a little trickier with the geometry, I'm going to start using vectors to solve these problems. So we can write all of these force vectors in terms of a magnitude and a direction. And I use these E hat, meaning a unit vector from D to F. Okay, so that's a unit vector from D to F, from D to E, from C to E. So from C to E, that's just a unit vector in the x direction. Okay. So now, how we can find these unit vectors is we can basically write vectors to the positions at the ends of each of these things. So the position vector to D, which is this point here, is LAC, this length, plus LCD, that length. And then the position vector to E, which is out here, this point here, is LAC plus LCE. And then to F, which is F is this position here. That's same x direct distance here, and plus LEF in the y direction. And then I make them have three components, so we can take cross products in the computer easier. So what we can do then is we can figure out what the vector from D to F. So from D to F is this vector here. That from D to F is that vector. And so we can find that by taking the vector from F and subtract the vector from D. And now what we want to do is make that a unit vector, because that's a unit vector from D to F, so we can just divide by its magnitude. And we can do that for all the other ones. So this one, we take the vector from E and subtract from E and subtract the vector from D, which is here. So that will give us this vector. And then we can normalize it to make it a unit vector, and we get EDE. And then ECE, if we just take the unit vectors between C, which I didn't see, is just LAC 0, 0, and E, so we can see that the difference is just this vector here, and normalizing it, that's a unit vector in the x direction. So we can do all that, and then we can just use summation. We can sum the force vectors, and I set that equal to 0 vector. And then if we break out in components, what we get is we get in the x direction, we get FCE, and then the x component of FDE and the x component of FDF. And in the y direction, we have, this is 4 kilonewtons and this totals 3 kilonewtons, so we get 1 kilonewton. And then the y component of FDE and the y component of FDF. And then we can just take moments, and we need to, I took moments about point A, which is here, or here, and so the vectors that create moments about that point are this one, and this one, and they all act at the same point, or act through the same point, and this is point D. So this is just RP, and we have that. We can find LCD just using geometry, and we can, so we have RD crossed with all of these vectors, and that has to equal 0. And if we do that, we get minus 4.8, and then 1.585 FDE minus, and then minus 0.449 FDF. That gives us our moments about point A. And now we have 3 equations and 3 unknowns again. Okay, and when we take this cross product, all we're going to get is the only non-zero component is going to be the one that's out of the page in the z direction. So this is the z component of this vector equation. And we can solve for our 3 unknowns. So we get FCE is 7.2 kilonewtons, FDE is minus 1.05 kilonewtons, and FDF is minus 6.39 kilonewtons. And so let's see if that makes sense. FDE is down, FCE is down at the bottom, is in tension. Yep. So we're expecting this thing to bend like this. So the bottom one should be stretched and the top one should be compressed. And that's what we got. And then the interior ones, which is FDE, it's hard to say what those would be. But it turns out that one is in compression.